All right, next example, example 2. We've got these 4 antiderivatives to compute. So let's take a look at part A. This part A is very similar in structure. The actual fraction here, this rational expression, is very similar to this expression right here. In particular, 1 over something squared plus 1. It's not exactly that, but we need to try to get it into that form. So we want to somehow write this as a single thing squared, which is actually pretty easy to obtain in this case. We can just write this as a 3x quantity squared. So then it looks like the thing that's being squared is 3x, so that should be a good choice for u. So du is 3dx. We don't have a 3 in our integrand, so we can divide that over to get dx is equal to 1/3 du. So then we should have 1/3 1 over u squared plus 1 du, which is 1/3 arctangent, or tangent inverse, whichever one you want to say, plus c. We'll back substitute. U is equal to 3x. So there we go. Part B. Now this one looks very similar to the sine inverse antiderivative that we have here. So this would be, let's remind ourselves, this would be 1 over square root of 1 minus something squared d something. So that's our goal here. So we want to get this into, we want to change this 9 into a 1, and we want to change this 16x squared into a single thing squared. So first thing I would do is always take care of this number first. If it's not a 1, make it a 1. Just like in part A from example 1, if you watched the previous video, we want to factor out a 9. That's how we can change that number that's not a 1 into a 1. We just factor it out. So you can do some of this off to the side if you wish as scratch work, or you can do it all within the same integral. It's really up to you, does not matter. So I would write this as the square root of, factor a 9 out, so I'm left with 1 minus 16x squared over 9, because we had to borrow a 9. There wasn't a 9 in there, dx. So of course, remember that the square root of two things multiplied together is equal to the product of the square roots. So we can distribute this square root over the 9 and this quantity in parentheses. So really, we've got square root of 9 times the square root of 1 minus 16x squared over 9. So this square root of 9, that's just 3. So we have a 3 in the bottom, so I can pull that out as a 1 over root 9, or more nicely, 1 over 3. So we pull that out, and then we're left over with just this single square root. And then I'm going to write this 16x squared over 9 as a single quantity that's being squared. So I would write this as 4x over 3. Because if we square it, we get 16x squared over 3. So that is what we are going to set for our substitution variable u. So let u equal 4/3 x. du is therefore 4/3 dx. And I'm just going to go ahead and multiply this 4/3, or divide by it, I should say, to this side. Technically, we do have a 3 in common, but at that point, we don't have the 4, so it's just easier, I think, to divide that over. And yeah, divide that over and then just import it that way. So we would have the 1/3 from the previous line that stays, but then we pick up this 3/4. And then we have 1 over the square root of 1 minus u squared du. Of course, the 3's cancel, and we have 1/4 the integral of 1 over the square root of 1 minus u squared? Well, this is in the specified format here, 1 over square root of 1 minus something squared with respect to that something. In this case here, that something happens to be u, since we performed a substitution. So this would become 1/4, because remember we still have that 1/4 there. But then this would become sine inverse, or arcsine of u plus c. And then, of course, we always back substitute. So u was 4x over 3. And there we have it. Okay. So the next example is part C. So we've got a definite integral this time, and we've got the 1 over 1 plus x squared. Well, really, addition's commutative, so 1 plus x squared is the same thing as x squared plus 1. So this actually is already in the format for arctan. So this is ready to integrate. No algebra needed here. So this is inverse tangent of x evaluated between 1 over root 3 and 1. So make sure that when you plug in these bounds, you don't just leave them as is. If you have the ability to figure these out, which you do because these are the correct ratios from the common angles. So anything that's a common angle, so anything that is a multiple of, pi over 6 or pi over 4, any multiple thereof, you should be able to figure out what sine, cosine, tangent, and their inverses all are for anything that has to do with those common angles. So 0, 30, 60, 90, 120, so on and so forth. So here, the inverse tangent of 1 is the angle on the unit circle where sine and cosine are equal to one another. So that would be pi over 4. Minus, we're looking for the angle whose tangent is 1 over root 3. So remember that tangent of an angle theta is the sine of that angle divided by the cosine of that angle. So if we take a look at the first quadrant, for instance, so also let's just remind ourselves that inverse tangent has a it only spits out things in this range here. So it only goes from negative pi over 2 of an angle up to positive pi over 2. So it goes like this. That's the range for arctan. So we're looking for some angle between negative pi over 2 and positive pi over 2. So notice down here all of the y values are negative. So since tangent is a ratio of these two terms, and the y value is of course always found by the sine of theta, right? So let's just remind ourselves here, this is the cosine of theta, comma, sine of theta. It can't be any angle down here, for if it were, then the sine of that angle would be negative and this ratio would be negative, yet we have a positive value here. 1 over root 3 is positive. So we now know we're looking at some angle here. So we really only have a few possibilities. We've got the 45-degree angle, we've got the 30-degree angle, the 60-degree angle, and we've got these two here. Okay. So really, if we think about these points on the unit circle, for the 30 degree, it is root 3 over 2 1/2. The 45 degree, it's root 2 over 2, root 2 over 2. And for the 60 degree, we've got the opposite of the 30 degree. They just flip. So this is 1/2, then root 3 over 2. So we want to divide these two pieces in the right order so that we get 1 over root 3. So clearly, it's not going to be this, because how would we get a root 3? So it's going to be one of these two, either the 30 degree or the 60 degree. So let's take a look at the 30 degree. So for the 30 degree, pi over 6, this would be the sine divided by the cosine. Division by a fraction is multiplication by the reciprocal. So this does work out to 1 over square root of 3. So that's how I would do this. So it looks like the correct answer here is that angle, pi over 6. Okay, so then we want to make this look nice and pretty, so we can go ahead and get a common denominator here. This would be, I guess we can do 12. So make this a 12. This would be 3 pi minus 2 pi. So this would be pi over 12. Okay. Moving on to part D. Taking a look at this, the bottom reminds me of arctangent. There's no square root, so this seems to give me an arctangent kind of vibe. But the arctangent form has just a 1 in the top. And actually, we could actually have any constant. For if we did, we could just factor the k out, and then we would have our 1. So the fact that there's this 2x term being added here makes me think it's not simply arctangent. So what we could do here is split the fraction by considering the bottom to be a single quantity. We can split this by dividing each term in the numerator by the entire denominator. So this would be 1 over 1 plus x squared dx plus the integral of 2x over 1 plus x squared dx. Okay, so this first term is just arctangent. It's already in that form, no other algebra needed. So there we go. This term here, the second integral, we would do a u sub. So we would let u equal 1 plus x squared. So du is 2x dx, and we do have that 2x dx matching. So these two things would, the 2x and the dx together would be replaced with a du. So this would become plus the integral 1 over u du, which of course is natural log of absolute u plus c. I could have added my plus c at this stage, at this line, but since we still had one more integral left, I just waited to add the plus c until the end. Doesn't really matter where you do it. So this is inverse tangent of x plus the natural log of absolute x squared plus 1 plus c. There we go.